All right, this problem is similar to number 8 on the chapter 4 review packet. Piecewise function here, g of x equals quantity 1 minus x cubed if x is less than 1, negative 1 plus x, quantity cubed if x is greater than or equal to 1. Part A, at what intervals is the graph decreasing? So what are we going to need to know to figure out when g of x is decreasing? Slope, right? So derivative, good. First derivative will tell us that. This first derivative is going to be what if the g of x graph is decreasing? Negative. So let's do the derivative of each of these. So g prime of x equals the derivative of x minus 1 cubed. We're going to use the chain rule. We're going to multiply by 3 out front. Take that exponent down to a 2. Copy down what's in here, so 1 minus x. Then by the chain rule, you have to multiply by the derivative of what's in here. So what's the derivative of 1 minus x?
Negative 1.
Negative 1. I'm just going to go ahead and put that negative right here. That's an important thing not to forget. And that's for x less than 1. Now let's do the derivative of the bottom expression. Multiply by 3 out front. Take the exponent down to a 2. Copy down your inside expression, negative 1 plus x. Then multiply by the derivative of negative 1 plus x. What would that be?
1.
1. So that's not going to change our sign. And that's for if x is greater than 1. I'm not going to put greater than or equal to 1 because I'm not sure that the derivative exists at 1. Because if these two graphs come together at a corner or a cusp, then the derivative won't exist. We're going to figure that out in a little bit here. Let's go ahead and make a number line chart for g prime. And the bottom numbers will be x. And one key number you have to put on the chart is 1 because that's where the functions switch. So we know there could be a corner, a cusp, or something crazy going on there. So let's put 1 here. If you plug 1 into the top expression, you get 0. If you plug 1 in the bottom expression, you get 0. So what's the derivative at 1?
0.
0. The left-hand derivative is 1. The right-hand derivative is 1. So the derivative at 1 is 0. If we would have got different values, then we would have said that the derivative is undefined. Okay? One thing we might want to check is make sure that the graph does actually match up, though, and make sure it's continuous at 1. If you put 1 into the original function, you get 0 and 0 also. So where do the two parts of the graph come together at?
0, 2.
At the point 0, 0. If you put 0 in here, you get, or you put, excuse me, the point 1, 0. If you put 1 in here, you get 0 for your g of x value. So these two graphs meet at the point 1, 0. Okay? Let's put some test. Let's see if is there any other value that would make this come out to 0 or undefined. Don't think so. 1 makes it come out to 0, and 1 makes this come out to 0. There's no other values that would make the derivative 0 or undefined. So there's no other critical values. So you don't put any other numbers underneath here. Now we're ready for test values. Put a number smaller than 1 in for x, like 0. Put 0 in here. You're going to get 1 squared, which is 1, times negative 3. Negative. Good. Put a number bigger than 1 in. And really, if you think about it, if you square a value, what type of answer are you going to get here?
Positive.
Positive times another positive. Positive. So that means the original graph of g of x is decreasing and then increasing. There'd be a minimum at x equal 1. The minimum would be 0, because if you plug 1 in here, you get 0. But that's not our question. Our question is, on what intervals is the graph decreasing? So you'd say from negative infinity to 1. Including 1. At 1, we're just going to say it's the graph is both of g of x is both decreasing and increasing. Any questions about that first part? Part B, at what intervals is the graph concave up? What do I have to look at to determine concavity?
Double.
Right. Second derivative of g. So let's do g double prime. I'll put it up here so it's kind of out of the way. Again, it's going to be a piecewise function. I'm going to start by doing the derivative here. I'll multiply by 2 times negative 3 is negative 6. Take that down to the exponent down to the first power. Copy down what's inside the expression, 1 minus x. And then by the chain rule, I have to multiply by the derivative of 1 minus x, which is what? Negative 1. So if I multiply by negative 1, that's going to make that negative 6 change back to positive. And that's if x is less than one. Oh, let me back up a second. The derivative does exist. It's 0 when x equals 1, so I do need to have a number line, or line right there. Okay, let's keep going here. Let's do the derivative of the bottom expression. So 2 times 3 is 6. Take that down to the first power. Copy down -1 plus x. Then multiply by the derivative of the inside expression, which is just 1. All right, let's make a second derivative number line chart. What number would make the second derivative come out to 0? 1. And again, notice when you plug 1 into either derivative, we get 0 both. So the left-hand derivative is 0 at 1, and the right-hand derivative is 0 at 1. So the derivative does exist at 1, and it's 0. Pick a number less than 1 to plug in the second derivative, like 0. 0 is less than 1, so we plug it in the top expression. What's that going to come out to? Positive 6. Yes, positive. Put a number bigger than 1 in, like 2 for x. That would be the bottom expression. Put a 2 in here, you get 1 times 6, positive. So on what interval is the graph concave up? Yeah, and be for all real numbers. It's gonna be concave up, even though the second derivative is 0. Probably gonna look something like this. Concave up, it's gonna hit a slope of 0, derivative of 0 at x equal 1. It's gonna be kind of like look like a parabola basically. Okay, that type of a shape. So concave up from -infinity to infinity.
You never use brackets with concave, do you?
Never use square brackets, right?